recorded to my. All right. So I think I've worked out all the internet issues. There were internet issues on campus, but I think they've been worked out. And I've got my iPad to share. I have a lot better opportunity to do the annotations with the iPad here at work. So I'm glad that I got that fixed as well. So when we last spoke, oh, by the way, I was able to fix the top hat. For some reason, it had them doing it at 12 a.m. instead of 11:59 p.m. I think I fixed all those. If you could double check that for me, that'd be great. All right. So the last time we spoke, we were talking about specific intermolecular forces. And these are forces between two molecules. And we talked about ion-ion and ion-dipole. And we had just started talking about the hydrogen bonding. All right, I'm going to admit some people here. And so the idea is that a hydrogen, which is the partially positive side of that bond, typically there's an electronegative atom bonded to it, and that electronegative atom has lone pairs. And so what that allows for is the ability for the acidic hydrogen bonded to an negative atom like nitrogen or oxygen or fluorine can reach out and be associated with, and we threw these here, the lone pairs on the electronegative oxygen or the electronegative atom on the neighboring molecule. Okay, in this case here, we have two hydrogens. I'm going to circle them in red. We have two hydrogens available for hydrogen bonding. Notice the hydrogens on the carbons are not available for hydrogen bonding because that is a non-polar bond. Okay, only the hydrogens that are bonded to electronegative atoms, like, I'm not seeing anything. Am I not sharing anymore? Oh, I'm not.
No, we can't see what you're circling.
Share. Okay. So, okay, can you see a slide that says hydrogen bonding?
Yes.
All right, and so we can see that now, and I'm going to erase all the writing that's on here. Yeah. Is the writing going away?
No, I think it's on a different slide.
Okay.
We're on the one that's talking about all the IMFs, where it says ion-ion, ion-dipole, hydrogen bonding.
Okay, done. All right, I am going to stop sharing. That is weird. That looks like it hung up on that. So let me go ahead and pull up those slides again. There we go. And I'm going to share my screen via cable. All right, so we see a slide that says hydrogen bonding, right?
Yes.
And it's got molecular structures on there. All right, so let's see, can I draw a circle on here? All right, am I drawing a circle on a hydrogen atom now?
Yes.
Okay, great. Whatever happened, I see the green border now. Yeah, I somehow got unattached, but I think we're working now. Okay, so the hydrogens that I'm circling here in red are available for hydrogen bonding because they are bonded to, they have a polar bond with an electronegative atom. The hydrogens on the carbons here, those are non-polar bonds. They do not hydrogen bond, okay? And the hydrogen bonding is between that the hydrogen here and a neighboring molecule with a lone pair. So there's an opportunity for a total of 6 hydrogen bonds. 4 hydrogens from 4 other molecules and the 2 hydrogens that are on that molecule. Okay, so those 6 hydrogen bonds are fairly strong, and that raises the boiling point of the system such that it is the highest of the set of these 3 compounds, even though they have the same molecular weight. So if we didn't have these forces, they would all have about the same boiling point because it would scale with molecular weight. Now, when we move to the next compound here, we have this hydrogen I'm circling in green. Hopefully it's still there. That is the only hydrogen available for hydrogen bonding because this one over here is now bonded to a carbon. However, we still have a total of 4 lone pairs for neighboring molecules to bond to. So that means we have 5 potential hydrogen bonding sites, 1 from the molecule itself and 4 additional ones from neighboring molecules. And that also significantly drops the boiling point. Notice we almost 100 degrees is less because we've lost that one potential hydrogen bond. And if we move it over such that we have no hydrogens, let me circle these in red here. If we move it so there are no hydrogens available to hydrogen bond, we only have those lone pairs. Okay, now those lone pairs do dipole-dipole interactions, but they do not hydrogen bond. And as such, it drops the boiling point down to 85 degrees. Okay, so you have to have two things for hydrogen bonding: a polar bond with hydrogen to an electronegative atom, like oxygen, nitrogen, and fluorine, and a lone pair on a neighboring molecule to make it happen. And it's the strongest one of these intermolecular charges we have. So if we move down in force, we go down almost an order of magnitude. We have what we call dipole-dipole forces. And we talked about how this is a polar bond where the oxygen is pulling electronegativity from the hydrogen to the oxygen because it's more electronegative. So that generates a partial negative charge on this side of the molecule and a partial positive charge on this side of the molecule. And I'm going to circle that in blue, because in these energy diagrams you're looking at here, the blue side is typically a partially positive, and that's a delta positive sign. And there is also the other side, which is usually in red, is the delta negative side. So how does this work? Well, if you have another neighboring water molecule come up to this right here, like let's draw it in this direction here. Okay, this is going to be the partially negative side of the molecule, and this is going to be the partially positive side of the molecule. The oxygen is going to be partially negative, and the hydrogen side is going to be partially. So when it comes to interact with here, that's a repulsive force. It's not going to do that. However, if we turn that around and have the positive side of a water molecule come toward the negative side of a polymer, that is our dipole-dipole force. Now, this particular molecule, water, can actually also hydrogen bond. But let's move over to the next molecule here. We don't have as strong a polarity on the bonds here. The chlorines are partially positive. The oxygen is partially negative. And because oxygen is just a little more electronegative, not that much more electronegative. So we're still going to have a partially negative side up here, denoted in red, and it's going to be attracted to the bottom, the dichloride side of an adjacent molecule. Okay, so that's why they're doing that, because it has a partially positive side and a partially negative side, and that leads to that dipole-dipole force. Now, this force is not as strong as the hydrogen bonding, and so it doesn't affect the melting point or boiling point. In fact, it kind of is lower in melting point and boiling point than any of the hydrogen bonders. So the last thing we have is a induced dipole, sometimes called a London force or a dispersion force. Okay, and basically you have a non-polar molecule next to a non-polar molecule. Okay, and to keep them from like repulsing each other just from having their electrons, what it's going to do is it's going to shift some of its charge to the opposite side of the molecule. So if we can look at this, this molecule here, it's going to be just this little ball of electrons coming up to another ball of electrons. However, to make this induced dipole happen, to give it some interaction, the neighboring molecule is going to shift some of its electronegativity away from the molecule that's coming toward it. And when it does that, we have a slight positive charge on one side of the surface. And there's that slight negative charge gets induced on the other one. And therefore, they have this weak attractive force. Okay. Notice then we have to have a molecule over here has to have the partially positive side facing it and the partially negative side. And so this is induced because it only happens when the two molecules are coming together. Okay. Now, because this is such a weak force, it's really controlled by the amount of surface area available to it. So if we have this N-pentane right here and this neopentane right here, they're the same molecular weight. Okay. However, with this long linear molecule here, we have a lot more area this red area here where we can have those little dispersion forces interacting with those two molecules. In the case of the neopentyl, it's actually almost spherical. And when it's almost spherical like that, it has very little surface area for it to interact with its neighboring molecules. And therefore, it affects the boiling point. Notice the boiling point of the N-pentane that's just a little bit longer is, almost 30 degrees higher than the boiling point of the neopentyl. So they are both nonpolar compounds. They both only have induced dipole-dipole interactions, and the surface area of them controls their boiling point. Okay, questions about ion-ion, ion-dipole, hydrogen bonding, dipole-dipole, or induced dipole, induced dipole?
Yes. I'm sorry, can you hear me?
Yes, I can. You hear me?
Okay. I had a question for the hydrogen. Yes, sir, I can hear you.
Okay.
For the hydrogen bonding, you mentioned that there had to be two things, and I only caught one of them. But it has to be a polar bond, and then what was the other one?
And the adjacent molecule has to have lone pairs. Because the hydrogen is the partially positive side, and it's going to be attracted to the lone pairs on adjacent molecules. All right?
Okay. Thank you. Yes, sir.
All right. So now we're going to tie this all together, the intermolecular forces and the physical properties all together. I said that there was some trending there, and I'm going to talk about it in a little more detail. And we're going to talk about the strength of those intermolecular forces between the molecules will determine how much thermal energy it takes to overcome attractive forces in order to make them melt or evaporate. Now, just the molecular weight alone allows the materials to slowly start gaining melting point and boiling point. Every time you add a carbon to a system, the melting point and boiling point increases. However, it increases much more rapidly as you include some of the other intermolecular forces. Okay. So that means that the different molecular forces have relative strengths and have different effects on that system. The other thing that we have with these intermolecular forces is that when we have materials that have similar intermolecular forces, they are more likely to dissolve in each other. Okay. Okay. All right. So let's go through these one by one and make sure we can see this. So, all right. So let's talk about melting point. Okay. The melting point is a colligative property that allows, it's the temperature where the molecules just stop vibrating. And so when they're in a solid, all they can do is vibrate. They can't slip past each other. And then once they can start slipping past each other, break whatever intermolecular bonding they have and move past each other, they now can become a liquid. Okay. Now, for things with ion-ion as the dominant force, these usually are very high melting solids. Think of all the inorganic materials you know that have salts, and they are really high melting solids. And so, because that's the strongest intermolecular force we have. Once we move down to hydrogen bonding, we now see that the things of equal or similar molecular weight significantly drops the melting point. The melting point is negative, it's below 0, so it's below freezing water, okay? And when we have that dipole-dipole interaction, that gives it a significant boost over no bonding at all. If we look at methane here, which is about the same weight, the London dispersion forces is all it has, and it boils at negative 182 degrees Celsius, okay? So that means the dipole-dipole interaction and the hydrogen bonding here are the two forces that are almost cutting that melting, doubling that melting point to get much, much closer to 0. Okay, so melting point is affected by the type of intermolecular forces you have. All right, so let's talk about boiling point. Now that we've melted our solid into a liquid, Now we're going to, so those molecules can now slip past each other easily, but they still have intermolecular forces keeping them a liquid. Now we have to break all the intermolecular forces to get from that liquid phase into a gas phase. And that's what we call boiling point. So we're breaking all intermolecular forces, not just the strongest ones to allow them to slip by each other because they still have intermolecular forces. Now we have to break them all. And so this takes us a significantly more amount of energy. And so in the case of our ion-ion compound, this is boiling at 1600 degrees C. So that's very, very high. Higher IMF, the molecular formula, empirical molecular formula. Yeah, the higher the mass, the higher the melting point, boiling point, and then the greater the force between molecules, even higher melting point. So let's look at this. So this has our strongest molecular force right here, our lithium and fluorine. And this has our weakest intermolecular force of our London dispersion forces. And so the boiling point of methane is minus 169 degrees. So that's it's a gas at room temperature. So that means it has very few intermolecular forces holding it together. Now, in contrast, moving to something about the same size, maybe a little heavier, with just dipole-dipole interactions, it's significantly higher, but it's still a gas at room temperature. And then once we get to that hydrogen bonding is the one that is our strongest intermolecular force in our organic compounds. We have a liquid at room temperature. So it's all about the strength of those intermolecular forces. Okay, so now that we have that, let's do a little bit more and compare things like this. Okay, so the first thing I want to show you on this is that all of these substances, we're actually starting with, oh no, there we go. All of these substances, we're going to start with just 7 atoms here. We're going to add atoms as we go. So the atoms are getting bigger and bigger. And we're going to look at how the forces change with that weight. Okay, so in the case of this compound here, all we have is a lone pair on this oxygen, and we have no hydrogen bondable hydrogens. So that means our primary force here is dipole-dipole interaction. So this partially negative side of the molecule is going to be attracted to this partially positive side of the molecule and control its boiling point. Okay, it's a very small molecule, and its boiling point is negative 24 degrees C. Okay. By adding just 1 carbon atom and 2 hydrogens, we've increased the molecular weight. We have not changed those forces. Okay, we haven't changed those forces. We now have that change in molecular weight with those dipoles. Our boiling point goes up. Okay, we haven't changed our force, we've only changed our mass. Okay, so that's showing it's increasing with that extra mass. Now, if we move up, add another carbon to the other side here, so now we have more than our original 7 atoms, we get a jump in the boiling point again. And once we start getting really long chains here, we actually have dipole-dipole as our primary, but we also get to start adding, the longer these chains get, we get to start adding the London force to it as well. So our boiling point goes up even higher. Okay. So this is showing that the dominant feature is the intramolecular force, but adding additional mass also increases our our boiling points and melting points. Okay. So to follow on with that, well, how can we use that to decide what's going to dissolve in what? Well, the primary intermolecular force also makes it the dominant force when it's trying to dissolve something into something else. So in the example here, like dissolve like, we have vodka is a mixture of ethanol and water, okay? Water, hydrogen bonds, ethanol, hydrogen bonds. Ethanol is 100% miscible. You could mix it in any portion from 100% ethanol to 100% water, and it will be all one solution. Okay, that's the definition of miscible. Okay, so we can use this dominant force of hydrogen bonding to make sure we can dissolve one liquid into another. Okay. So, but they have some limits, okay? And I'm going to pull this over here, okay? So if we look at methanol, it's a small molecule and it doesn't have a very nonpolar side, but it has a lot of hydrogen bonding with that OH there, okay? And because of that, it's completely soluble in water, completely miscible in water, but it barely dissolves in hexane. Hexane is a nonpolar organic solvent. But by adding one extra carbon here, we now have our dominant feature is still the hydrogen bonding, but we have an available size fragment here that can van der Waals force or London dispersion force, is that induced dipole-dipole. That makes it soluble in hexanes, but the hydrogen bonding side makes it soluble in water. Okay, let's add one more carbon, see if it changes again. Right here, all we've added is one more carbon here. So now we have 3/4 of the surface area of that molecule is available to van der Waals bond. And 1/4 of it is available to hydrogen bond. So we have infinite solubility in water and infinite solubility in hexanes. Okay, so they're completely miscible in both. Let's change our structure one more time. Now we have 4/5 of our surface area is now van der Waals force driven. Only 1/5 of our surface area now has that hydrogen bonding. And what happens? We lose solubility in water and we gain we are more soluble in hexane. And then as we add more and more, we continue to get lower and lower solubility in water and more compatibility with the non-polar solvent, okay? So this is saying that, well, the hydrogen bonding is our primary interactive force, is our stronger interactive force. Once you start getting to having less and less of the surface area of the molecule available for that force, the other forces begin to dominate. In this case, the induced dipole. So this is miscibility or solubility of two liquids together, okay? However, we can do that kind of control with different things as with solids and liquids too, all right? So the idea here is if we want to think about a generalized scheme here, if we have ions right here, an ion can never be a solid. Ions aren't liquid at room temperature, except in very special cases. So we're not going to do that. However, if we have a hydrogen bonding solvent and an ion, we can actually almost all ionic solids do dissolve in hydrogen bonding solvents. There are a few exceptions like silver chloride, but they do have very high solubilities in these hydrogen bonding. Now, the ions can be soluble in things with a dipole, okay? If that has a strong dipole and if the ion is fairly big and fluffy or has a large surface area, you can get some of those in there. But if the ions get really small or the dipoles get really small, they become insoluble. And with this induced dipole right here, you have no solubility of ions because there's no compatibility there. So now if we had a solid or liquid hydrogen bond, it's going to be very highly soluble in hydrogen bonding solvents because like dissolves like, until you get to the point where the induced dipole becomes the greater part of the surface area. Okay? Now, hydrogen bonding with dipole, it varies. The dipole can be strong, the hydrogen bonding can be weak, so it really varies quite a bit. And when we go to hydrogen bonding in dipoles, it tends to have low solubility, mid to low solubility, because the hydrogen bonding is a stronger interaction than the induced dipole, and so it's not as compatible. With hydrogen bonding, these kind of go together. They're variable solubility depending on how strong the dipole is and how strong the hydrogen bonding are. However, dipole-dipole is highly soluble in other dipole materials. So that's really good. And they tend to also have the induced dipole be soluble in that dipole material because it can do an induced dipole with one compound and the full permanent dipole with the other compound. And that yields the solubility parameter. And likewise, the induced dipole and the using the induced dipole as the solvent, you can dissolve things with dipoles. And of course, using a induced dipole as the solvent and as the solute, that is also very highly soluble. So dominant forces control boiling point, melting point, and miscibility and solubility. Questions on that? Oh, sorry, my camera's over there. Okay, so that brings us up to one of the weirder ones is that what if you have a molecule that's both? Okay, so you have a side of the molecule that likes water or is hydrophilic. So think about, something that hydrogen bonds like a carboxylic acid. And then you have something that's hydrophobic like hexane, okay? So in theory, your fatty acids that do this would be insoluble in just oil or insoluble in just water. However, because the different zones can be self-segregating into their system, we can end up with what we call a micelle. And in this case right here, the hydrogen bonding side of the molecule here is going to stay in the hydrogen bonding liquid surrounding it. The van der Waals force part of the molecule is going to dissolve in the other van der Waals force molecules together. And that creates a sphere of charged water-loving species on the outside and non-charged, non-polar material on the inside. And so this is actually how soap works, because the oils and stuff that get dissolved into the center of the non-polar section, while the polar group here keeps it suspended in the water and washes it away. All right, questions on that? Okay, this is the end of chapter 1, talking about molecular structure and bonding. Okay, make sure you understand that sigma bonds are 2 electrons shared between 2 atoms. The bonds can be polar or nonpolar. We only make double bonds with p orbitals, unhybridized p orbitals. Know your hybridization, and know that hybridization changes electronic structure and molecular structure. So those are very important right there. And then after we learn that in the molecular structure, knowing what kind of forces between molecules and how they vary their properties. Those are the highlights of chapter module 1. Okay. All right, I'm going to move on to module 2. Nomenclature. Okay, so the cool thing about nomenclature is it's a nice, precise system in which we can use a set of rules that when I write a name of a compound, you could draw the name, you could draw that compound correctly because there were nothing ambiguous about the system. And if you draw it about that, then we can do I can write the name of it and it would be unambiguous. So let's talk about that a little bit. Okay. We want to first understand that there are structural differences between different kind of compounds. We're going to start with the hydrocarbons. Okay, the alkanes, the alkenes, and the alkynes. We are also going to talk about functional group. And the reason we're talking about functional group is because functional group changes what it is, what that molecule is named for. Okay, and then we're going to learn about the IUPAC rules, which is the International Union of Pure and Applied Chemistry, that allows us to have unambiguously identified each and every substituent and molecule such that it can be understood anywhere in the world. Okay. So the first thing I want to talk about is that there are several parts of a name. Okay, so in that several parts of a name, we have the prefix, which is all the things that are attached to that parent number, that parent molecule, the parent chain, and I'll talk about that. It also tells us about the number of carbons in that parent chain. So that parent chain is what we're going to be ending up naming the bulk of that molecule for. The next thing we have is what we call the infix. The infix tells us whether we have a single, only single bonds with carbons, or if we have at least one double bond with carbon, or if we have at least one triple bond with carbon. That is found in the infix. And then the last thing that we have is the suffix, the thing tacked on the end. The thing tacked on the end tells the class of the compound. In this case, we're going to start with alkanes, alkenes, and alkynes, and we're going to go from priority to priority. This is a great opportunity to go ahead and go to Canvas, download my nomenclature guide and the document called Functional Groups You Should Know. So this would be great to, get those two documents in your hands and start using those as we go forward. Okay, so when we talk about functional groups, we call them functional groups because they're the part that's typically going to do the reaction, okay? Carbon-carbon bonds and carbon-hydrogen bonds are very non-polar, okay? So if they're very non-polar, that's not going to be very reactive. So we're looking for polar bonds, double bonds, triple bonds, things where we can make reactions happen. And that defines the class of functional groups we have. So if we look at these functional groups here, and these are some ones that we will be getting to out throughout the rest of the semester, we're going to focus on this first column for this semester. These are things we'll probably doing that one too. This semester, we're going to focus on this, and we'll be doing a little bit of aldehyde and ketones, but all the carboxylic acid stuff will be done next semester. Okay, so what we want to look at for are things like alkyl halides. Okay, an alkyl halide has a halogen that usually acts as a leading group. Could be chlorine, bromine, or iodine, occasionally fluorine. Anything with a double bond in it is called an alkene, and that's typically where the reaction happens. Things can add across it, or things can react with it or break it apart completely. An alkyne is a triple bond. And so these first two are the hydrocarbons here. They're predominantly just carbon and hydrogen bonds. And now once we move to adding other atoms to it, we get new functionality. If we have an oxygen in there that can hydrogen bond, it's an alcohol. But if we have an oxygen that can't hydrogen bond because it's bonded to two carbons, we call that an ether. And we can even use sulfur in this system. It's an electronegative atom, and it would be called a thiol if it has a hydrogen bonding hydrogen, and a sulfide if we take away that hydrogen bond. And then aldehydes and ketones we'll talk about when we get there. Now, why do I care that we know about some of the functional groups we start with? Okay, the reason is when we start naming our groups, it all depends on what's the highest priority functional group, okay? So in the case of this, the carboxylic acids and the carboxylic acid derivatives right here are the highest priority group. Luckily, we're not going to study them until next semester. So everything from here up, we're not going to study till next semester. But you will see that those are going to get us the highest priority, and all of the compounds will be named for those functional groups. But let's look at the lower end of the spectrum where we're going to be dealing with. When we have functional groups like a nitro group or an aryl group that's pendant to a chain, they don't change the name. They are just substituents and they're low priority. That goes true for halogens, other alkyl groups or ethers. Those don't change the name. They are still going to be hydrocarbons of some sort. The only time we start changing the name is when we've changed the nature of the carbon-carbon bonding. And then when we add nitrogens or sulfurs or oxygens to the system, it starts changing the name and we get to higher and higher priority. And I'll explain that as one of the rules we have in our system. Okay, so this is a great review for you to go out and start, learning these functional groups and what they look like. And notice on the diagram I show here, I have the lone pairs there. And because we're actually going to end up you know, those lone pairs are going to contribute to the reactivity. So this is why I have that out. Looks like all the questions in the chat are about SI, so I'll let Marcus handle that. Okay, so the first and simplest group are what we call hydrocarbons, okay? They only contain carbon and hydrogen, no oxygen, nothing else, okay? So this is our simplest kind of molecules, and this is where we're going to start. So in the case of hydrocarbons, we have different types of hydrocarbons. So when I'm thinking about different types of hydrocarbons, we're going to start with the simplest one, okay? The simplest one we have are what we call alkanes, A-N-E, that's the key here, alkane, A-N-E at the end here, okay? These are all carbon and hydrogens, and all the carbons have single bonds, okay? Now, if we have at least one carbon-carbon double bond, we move up to the alkenes, E-N-E, okay? E-N-E, that's the key phrase here. And if we have even one triple bond, we go for the Y-N-E. So those are alkynes, okay? So even though they're all hydrocarbons, that nature of the carbon-carbon bond changes the functionality of it. Think about it, the alkanes have only carbon-hydrogen bonds, not very reactive. That double bond's more reactive than anything in the alkanes, and that triple bond is more reactive than the alkenes or the alkanes. So we're adding reactivity, so we're changing the name of the system. We also have another kind of compound called aromatic, and we'll study these in the second half right here, but think of structures that look like benzene, where you have alternating single and double bonds. They don't have to have they don't have to have 6 carbons in them, but a lot of them do. So let's continue down the road of looking at hydrocarbons. So I said before, we're looking at the ANE. The ANE here is the critical thing we're looking at. This ANE is what we're going to call our infix, okay? So the AN is our infix, okay? And the E at the end is our suffix, okay? And it's our suffix because all alkanes have an E at the, all hydrocarbons have the E at the end because that's its class. Its class is defined by the E at the end. Okay.
Wait, so you said the AN is just the infix, or
the AN is the infix.
Okay.
The E is actually the suffix. Okay. And it becomes clearer as we go add more groups. Okay. Let's see. So there are no double bonds, no pi bonds at all. And the general formula has it as we're going to take every carbon gets 2 hydrogens on it. And then at the ends of the chains, we're going to add 2 more hydrogens. So what that ends up giving us is a generalized structure of however many carbons you have, you're going to have 2 times plus 2 of those hydrogens. So let's think methane, which would have 1 carbon. So we have 1 carbon and 2 times 1 is 2 plus 2. So we'll have 4 hydrogens, okay? So that's one of the simplest ones. And then as we build up, we're going to change the prefix based on the number of carbons we have, okay? So let's look at our infix here again. It's the AN. And then this E is our suffix, but our prefix here is prop, okay? What we're gonna learn on the next slide is that that number, that name there, signifies the number of carbons in our longest chain. So 3 is prop, 4 is bute, and 5 is pent, okay? And so there's about 5 or 6 of these you'll have to learn, but the rest of them kind of follow a nice system, okay? So that first part of that is our prefix, the AN is our infix, and the E is our suffix. Okay, so let's talk about what those names would be. And the ones that are a little bit hard to remember are going to be the first few here, the 1 through 4, okay? Because 1 carbon is called meth, not like crystal meth, but just meth. And so its alkane name would be methane. So then we have eth, prop, and but for 2, 3, and 4. Okay, so those are the ones you probably have to remember. And so that's ethane, propane, and butane. After that, it becomes that nice numerical system. Okay. There's a mnemonic. Somebody actually just put a mnemonic in the chat room there. Mary eats peanut butter is a good way to remember methyl, ethyl, propyl, and butyl. 1, 2, 3, 4. Okay. Then the rest of them follow that nice, I think it's a Roman pattern of penta, hexa, hepta, octanana, deca. And so once we get above deca here, un means 1. So undecane is 1 plus 10, 11. Do means 2, tri, tetra, penta. So we just keep adding those up, and those go up to 20. The last one I want you to know is the icosane. That's 20 carbons. Okay. So I think those are the ones that might need some remembering. Everything else follows a nice pattern. Okay. Now, the next thing I need to do is define parent chain. Parent chain is the longest continuous uninterrupted of carbons in your compound. Okay. The longest continuous uninterrupted chain of carbons in your compound. Okay. So that's our parent chain. Okay. And that gives us our number of carbons is our prefix. Our AN tells us we have no double bonds, and our E tells us we have a hydrocarbon. So those are the 3 parts of our simple names that we'll continue to add on to. Okay, so if that's the parent chain, why do we care? Well, because we need to know what the longest chain is so that we can figure out what's attached to it. Anything that's not part of that parent chain is a branch, okay, or what we could call a substituent. Okay, so that we have to locate where that branch is correctly on our parent chain because it adds carbons, but it doesn't follow the name because it is a substituent, and we need to identify it as such. So what we can think about is our longest continuous carbon chain is going to be our, let's do our trunk of our tree. So you'll find your longest chain, and then that goes to the end, whatever your suffix is, icosane right here. And then we have to start thinking about what size, how many carbons are in each of these, and where are they located on the molecule. Okay, so when we talk about substituents, we're going to first start talking about substituents that are just hydrocarbons, and then we're going to expand upon that as we add more and more functional groups. But in this case here, substituents are carbon or hydrocarbon chains that are not part of that parent. Okay, and we have a couple different types we have. One of the things we have is what we can call unbranched, meaning that it's just another straight chain off of that main parent chain. The other thing we can have are what we call branched. So we have a straight chain coming off, but then we have another substituent on that other chain. Okay, so imagine a branch on a branch. Okay, so that's the branched substituent on the system. Just having a single limb on there is unbranched. Okay. So we still have to know that we have those carbons on our system, but they're not changing the name because only the parent changes the name. Okay, so let's define that a little bit. Okay, so when you have a substituent like this, we have to figure out a way to correctly name it. And so what we're going to do is we're going to take off the ANE because that's telling us it's a parent chain. We're going to count the number of carbons in that substituent, and then we're going to use the prefix for the number of carbons. We're going to add the YL. So if this would have been ethane with just 2 carbons in it, it becomes the ethyl group when it's a substituent because we have 2 carbons, 1, 2, attached to the parent chain here. So it's the ethyl group. And if we just had 1 carbon there, it's the methyl group. Okay. So the YL signifies a hydrocarbon chain that's a substituent. And so we need to know that is how we know that it's a substituent. Okay. So Are there some rules associated with this? Of course. We need to make sure it's unambiguous so everybody has the same rules and everybody follows the same rules. So the first thing we do when we're naming these things is we find the parent chain, okay? So in this case, we've already found the parent chain, and it's this one right here. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? It's not always in a straight line, and I'll show you an example of that. But now we have to look at our carbon attached directly to the parent chain, right here. That's where we have to start numbering our substituent, where it attaches to the parent chain. We're going to number the parent chain based on a different rule, but when we name alkyl substituents, it's starting from 1 is where it's attached to the main chain. And the longest portion of this chain is 4 carbons. So that means that we have at least a butyl group here, but then it also has another substituent. Okay. Now, notice that we've identified this as our number 1, and now we know our substituent is on the number 2 carbon of our substituent on our parent chain. So we're going to have to use a variety of numbers and words to describe our substituents in a consistent way. So let's talk about classifications of atoms now, okay? So the key with the classification of atoms is, number 1, it tells us where things are, and number 2, it kind of gives us a good way to look for similarities in, oh, will it react like this side or this side? And it's all based on their classification. So if there is nothing attached to the carbon, if it's methane, it's just the methyl, okay? It's not primary, secondary, anything, it's just methyl, okay? However, if you have one other carbon attached, you become a primary carbon. So we can think of the ends of a chain right here being our primary carbons. Okay. If you have 2 carbons attached, it's a secondary carbon. So you can think about the bends in these long chains. All of, let me draw them in a different color. Red here, that's a secondary, 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 because there are only 2 other carbons attached to that system. But once we go to 3 other carbons, we're going to end up with tertiary right here. So we have 1, 2, 3 bonds to it. And remember, don't forget that hydrogen, that assumed hydrogen. But we're talking about classification of carbons. It's how many carbons it's bound to. Which brings us to our last one, which I'm going to do in purple right here. That's our quaternary right here. Notice we have 1, 2, 3, 4 different carbon atoms bound to that, and that gives us our quaternary carbon. So we're going to use this nomenclature to help us identify some of our substituents, as well as use it for identifying the most stable structures we have in our materials as we move forward. Okay, so let's talk about how we're going to use it first to help us name our substituents. Okay, so the first thing we're going to do is we're going to look at our simplest substituent we have, and that is the methyl group. And we don't have any isomers available to it. It's just going to be methyl group. Ethyl group, we don't have any isomers available to it. It's just going to be the ethyl group. However, once we get to 3 carbons right here, the propyl group, and so this is showing that that's the substituent. So it's attached to the main chain right here. This is our main, oh, sorry, the parent's on the other side. Our parent is attached to the other side here. And so our parent is attached to this side right here, which means we have 1, 2, 3 bonds in that. And because that's where it's attached, this is the number 1 carbon, the number 2 carbon, and the number 3 carbon of our substituent. Okay. So, but because we have 3 atoms, we now have a possibility for a different isomer. Okay. And so our different isomer is commonly known as isopropyl. So we still have 1, 2, 3 carbons. This is still our 1 carbon. This is still our 2 carbon, but now we have a branch, and this is on this branch, this methyl group is on our 1 carbon. Okay. So our methyl right here is on our 1 carbon of our ethyl attachment, because our ethyl is the longest chain. Right here, 1, 2 carbons, gives it the name of its substituent. We have the substituent that's on that. So we have 1 locating the methyl group on that ethyl chain, and then the ethyl is the longest chain in that substituent. Now, the word iso right here comes from isomer. And so you can think it's propyl, and then it has one isomer, and we call that isopropyl. Okay. Okay. There's also another one where you can actually have it, you get the same kind of thing when you add another carbon here as a molecule by itself. It's also called isobutane. So when you're looking at anything that has that kind of structure there, think about iso as part of its name. Okay. Now, when we move up one more carbon, we actually have more available isomers available to us. If it's just the straight chain hydrocarbon here with the parent here, and we have 1, 2, 3, 4 carbons, that's the butyl group, right? 4 carbons is butyl. And if we branch them, we can branch them in a bunch of different ways. Now notice this looks a lot like the isopropyl right here and the isobutyl here. So that's why we call it the isobutyl attachment. However, if we were to name it by IUPAC names, remember we are going to number from where the substituent attaches to the parent. So that'd be 1, 2, and I'll pick that one as 3, meaning this remaining methyl group is on the number 2 carbon. So our IUPAC name is going to be 2-methyl, and we have 1, 2, 3 carbons left for our propyl substituent. So common name is isobutyl because of this those three carbons attached to a central carbon. But the total name is 2-methyl propyl. Right here is the full substituent name. Now, let's move that methyl group from that 2 carbon to the 1 carbon, okay? When we move that 2 carbon to the 1 carbon, what we end up with is a different compound. So now this is our number 1 carbon, our number 2 carbon, our number 3 carbon, and our methyl group is now there. Now, this gives rise to the idea that this carbon that's attached to the parent chain is now a secondary carbon before it gets attached to the parent chain. Okay, so we have 2 things bonded to it here. So we call that sec-butyl. Okay, so before we attach it to that parent chain, it had a secondary carbon, so it's sec-butyl. Now, if we're going to do the IUPAC name, we know it's on the 1. This methyl group is on the 1, so it's 1-methyl propyl. Okay, and we can do one more isomer by changing all of the groups into methyl groups. And this isomer is called, would have a tertiary central carbon before we attach to the parent chain, and therefore it's tertiary butyl, right there. But the IUPAC name, because our longest chain is now 1 carbon, 2 carbons long, and then we have 2 methyl groups right here. It's going to be 1,1 dimethyl, there should be a di here, 1,1 dimethyl ethyl as our substituent. So see how we're building up a series of rules that we apply each and every time? Okay. All right, so let's go with our last one. And these are the last 2 you'll need to know. Pentyl's easy because it is just the straight chain of 5. But now, once we get this structure here, that looks a lot like the isobutyl and the isopropyl. So we call it the isopentyl. Occasionally it's called isoamyl. I think isopentyl is more common. But if we were to number this from the parent 1, 2, 3, that remaining methyl group is on the 3 carbon, so it's 3-methylbutyl. Okay. The other way to do it is to have like a tertiary butyl part here with another CH2, and we call that 2,2-dimethyl propyl or neopentyl. So that isopentyl and neopentyl are the last 2 common names for substituents you should devote to memory. Okay. And another way to look at that is this compound right here, which is not a substituent, it's an independent compound, is called neopentane. And so the only difference is that it's attached to a parent chain on one of these methyl groups. Okay, so that's one good way to look at how that is attached. Okay, so we've done longest chain continuous of carbons. Okay, And now we know things can be attached to it and they're substituents. And the substituents can be straight or branched, okay? So now we've built up levels of complexity, but we have rules in place to make sure we can assign them correctly, okay? So now let's enumerate these rules so that we can make sure we all have them in the same place at the same time. Number one, identify the parent chain, the longest continuous number of carbons. Second, identify the substituents, all the different branches coming off, identify them and name them. Assign a location to each of the substituents, and that's the rule I'm going to talk about next. Name the compound and list the substituents in alphabetical order. Okay, so let's talk, we've done 1 a little bit, we've done 2 a little bit. Now let's add 1, 2, and 3 together to see if we can't start naming our compound correctly. Okay, so the first thing we need to do is we need to make sure we count the right number of carbons as our longest chain. Okay. So in this case here, we have to just know that it's the longest number, but we don't ambiguously start at the right or the left when we number. Okay, we have to figure out which one it is as we go. So in the case of this structure here, we have this one labeled on this left side, the red side here. We started over here on this end and started labeling 1, 2, 3, 4, 5, 6. And then we labeled our substituents as, oh, there's a methyl group, there's a methyl group, and there's a methyl group. Okay. So the first substituent here showed up on the number 3 carbon, and the second substituent showed up on the number 5 carbon. Okay. However, that's not what we do. We want to have the first substituent encountered be the lowest number, okay? Which means we did not number this correctly. If we to renumber that same molecule from the other side, where 1 is on this side, and naming it in that direction here, our first substituent we come to, which is a methyl group, is on the 2 carbon. Okay, so that's important. We always want to have the first substituent as the lowest number. So now we know which way to number our systems. Now we can locate all the different types. Now, I said before that we had 3 methyl groups here, okay? So they're all the same methyl group. So we can clump them together and say it is tri-methyl compound, okay? So we can do a di for 2, tetra for 4, penta for 5. So it makes it easy to say, okay, we have 3 methyl groups, but we still have to identify exactly where each of these are. And we do that with a number, okay? So if we blow up this part here, we're gonna start numbering from this side again, right here. We're gonna start with 1, and our first substituent is on 2. So we have a 2 methyl, and then the next one is on a 4, and then the next one is on a 4. So when we have numbers, we wanna do the number plus a comma, number, and a comma, number, and a comma. Wait, we don't have to have a comma. But when we separate numbers from letters, we put a dash. Okay. So we have 1, 2, 3 methyl groups, so that's trimethyl. So our correct name is 2, 4, 4 dash trimethyl, and then hexane, because we had 6 carbons in our main chain. Notice the words run together, okay? When we're naming substituents, numbers are always delineated or separated by commas. Numbers and letters are always separated by a dash. But the rest of the numbers can run together. Okay, doing good on time. Okay, so what if they're not all the same? Let's go ahead and establish a rule for that right here. So once all of the substituents have been identified with their location based on having the first substituent be at the lowest number, we now need to think about how we put them in order. Okay. So if we had more like an ethyl group, a propyl group, and a methyl group, okay, we have to alphabetize them when we put them in names. So if we just had the methyl groups, we didn't really care, but now that we have a methyl, an ethyl, and a propyl, on our group, we need to, and we know that the methyl is on the 1 carbon, the ethyl is on the 2 carbon, and the propyl is on the 3 carbon. Okay, we need to arrange them in order such that they are alphabetized. Okay, so, but we don't include words like di and tri as the alphabetization. It's only the hydrocarbon chain we're looking at. We also ignore things like sec and tert, but not when it's the word like isopropyl or neopentyl. Okay, so if there's a dash there, if there's a hyphen there, it is not hyphen. It's not alphabetized. Okay, so if we're going to apply this rule, so we've identified where the different substituents are with their numbers. Now let's write them in correct order based on their alphabetization. So if we were to name this compound with just these substituents on there, we would go 2-ethyl dash MNOP. So M comes next, 1-methyl dash 3-propyl. There's an O there. Okay. So see what I've done? I have the number for the substituent on where it's located. I have the substituents all in alphabetical order, and I've separated the substituents, the letter from the number with a dash. Okay, so I followed all those rules to get this in order. Okay, so now that we've got those in order, let's go ahead and see a couple other rules. Like maybe, what if the substituents would be this, you would have the first substituent if you numbered it either way, okay? So in this case here, we have the first substituent appearing at the 2 carbon right here, or the 2 carbon coming from this one, okay? So, that's ambiguous, right? Because you have your first substituent, okay? Well, now you need to go to your second one. You need to have that second substituent be at the lowest one. So if we come from this side, right here, we have a 2 as our lowest number, but then we have a 4 and a 5, okay? Let's number it the other way and just make sure. And when we number it the other way, we started with our 2 as our first one, but our second one is at our 3. So we always choose the second number. The first one didn't give us a unambiguous numbering system. The second one did. So that means the correct name for this is going to be 2,3,5 trimethyl hexane, because we could, just going this way, we would have had a 4. Coming this way, we have a 3. So that makes it a lower number, which makes it the way in which we're going to make these. Okay. And now let's talk about naming the whole thing, okay? All right, so the next rule we want to talk about is if we have a number of branches and if we have 2 or more parent chains that are the same length, okay, we want to choose the parent chain that gives us the greatest number of substituents. The reason for this is then your substituents are going to be less likely to be branched, and it'll be easier to name them. More substituents, the correct number of the correct parent. So let's look at what parents could be here. And so if we just started here and tried to go along here, we can go, oh, look, that goes 1, 2, 3, 4, 5, 6, 7, 8, 9. Or we could have taken that same path and gone to here and get 9. Or we can take this path right here and also get to 9. See how all 3 of those would terminate in 9 carbons being in our longest chain. Okay, so now we're going to choose the one that gives us the greatest number of substituents. So in that case, it turns out that if we look at the one with the green here, we're going to have 1 substituent, 2 substituent, 3 substituents, 4 substituents on the, on the yellow right there. On the green, we'll have 1, 2, 3, 4 as well. And on the blue, we'll only have 1, 2, 3. Okay, so that means we have to choose the yellow or the green. Now, let's choose between the yellow and the green. Turns out they're exactly the same because they have the same end of the group. So we just have to pick one or the other. Now, when we look at this here, I said before, don't always look for that main chain being in a linear line. It's not always there. In fact, in this case, it's not in a straight line. So we're going to follow this as our main chain right here. And it's not in a straight line, but it is our longest chain of 9 atoms. Now, let's use those other rules and name it correctly. So if we pull this up, we have our first substituent would be on the number 2 here if we numbered it from this direction. Our first substituent would be on the number 2 here, and they're both methyl groups. Okay. However, and this would give us a 2 here, and this would give us, a 3 here, and this would give us a 3 here. So that's the same. 4, 5, 6. Okay. No, so, yeah, 6, and then 7. Okay. And it turns out, gosh, those are all the same going from one to the other. Oh, no, actually, I did that wrong, didn't I? That would be 3, 1, 2, 3. So we have to label it from the right to the left. So our first part is 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 9 gives us nonane right here. Now let's look at our substituents. We have 2 ethyls and 2 methyls. So we get to use diethyl and dimethyl. However, we have to put ethyl and methyl in alphabetical order based on ethyl and methyl, not the dyes. So now let's figure out where the ethyl groups are. Our first ethyl group is on a 3. Our second ethyl group is on a 6. So we're going to have 3,6 dash diethyl. Now our first methyl group is on a 2. Our last methyl group is on a 7. 2, 7, and there should be a dash here. Dimethyl nonane. Okay? See how following all the rules in order, we can get to an unambiguous exact choice. Okay, questions on that?
I have a question.
Yes.
I just want to confirm, you said if you find that you have 2 options of longest parent chains, you then go to the parent chain that gives you the most substituents.
Correct.
Okay, and then after that, we had 2 options of parent chains that would give us the most substituents, and we just numbered it based off of the giving the substituents the smaller carbon numbers?
Yeah, and in this case, we could have chosen this carbon or this carbon to do that. It turns out it'll give it the same number. So if, but you need to identify, make sure they give you the same number, and then you can just choose one.
Okay.
But and then the numbering from which direction is all controlled by the lowest substituent first.
Okay, thank you.
Okay. Now there's a subtle caveat to that lowest substituent first, and that's if you have a methyl group and an ethyl group both at the lowest number, you actually do it with the 1 in alphabetical order first. So you'd actually number to the ethyl first through the ethyl first. That's the only subtlety on it, and that's on the other rule. I'm sorry, that's on the nomenclature review online, so you can see that there. All right, so this has all been for linear right here. And so when we join again, we will be, it's 1:40 right now. And so that's the end of our class for today. Or is it 1:50? Can we have 1:50? Right.
Yeah, it ends at 1:50.
Okay, great. Now let's go to, what if we have rings? Okay, well, we can easily have lots of hydrocarbons that don't have just the linear thing, but they have a ring. And that means we still only have carbon-carbon bonds and carbon-hydrogen bonds, okay? But we call them cyclic alkanes. So cycle meaning ring, alkane meaning only carbon and hydrogen, and no double bonds. Now, our general rule, our general molecular formula changes, because imagine you have a long chain, you pull a hydrogen off each side and link those 2 carbons together. So we've lost 2 hydrogens to make that ring. So our general structure is only the CN 2 times N. So if we have 6 carbons, we're gonna have 12 hydrogens. Okay. And then we use the term cyclo in front of the number of carbons in the ring to give us our parent chain. So if you have 6 carbons in the ring, you have cyclohexane. If you have 7 carbons in the ring, it's cycloheptane. Okay. All right. So now, if you have a substituent on your ring, you need to figure out how long your substituent is, okay? Because the longest chain, even if you have a ring, the longest alkyl chain controls the name, okay? So in the case of the one on the right here, the substituent only has 3 carbons in it. It's a cyclopropyl, okay? However, the main chain has 4 carbons on it, okay? So that straight chain has 4 carbons. The 4 carbons is longer. It is the parent chain, and therefore we have our butane, and then we have our other carbons as a substituent. And in this case, because it's hooked onto the first carbon here, it's 1 cyclopropyl as our substituent. However, if the cyclic compound has more carbons than the substituent, it's named for the cyclo compound. So it's just like the parent ring. It's just if it's in a ring or not, the longest chain wins, and then the other part becomes the substituent. And in this case here, it would be 1-propyl cyclohexane, because we have 6 members in that ring and only 3 members in this ring. Okay, does that make sense? Okay, so when we number cyclohexanes, if there's only 1 substituent on there, that's easy because we just assume wherever it's attached is number 1. Okay. However, if you have more than 1, it gets a little complicated. Okay, because you need to look where the first substituent is encountered. If you only have 2, you have the first substituent and the second substituent. But if you have 3, you have to find where the first 2 substituents are, just like we did with those longer chain alkanes. In the case here, we have 2 methyl groups on the same carbon, and then we have a 3rd substituent way over here. So that means we get to start with those 2 methyl groups as both being on the same carbon, so that signifies it as our number 1 carbon. Even though ethyl is lower in alphabetical order here, we're not going to start with the ethyl group, so this is wrong. So we're going to end up with 1, 1, 3. So in this case here, after we alphabetize, we have 3-ethyl-1,1 dimethyl cyclohexane. So highest number of carbons here. Each of these pendant chains has less than 6 carbons, therefore they are substituents.
Wait, sorry, I was a little lost on why the dimethyl has priority, just because there's 2 of them?
Because that's the first 2 substituents. So if we're going around the ring and we look for the first substituent, it's this methyl group. But with the second substituent is also a methyl group. So because this counts as 1 substituent and this counts as the second substituent, they just happen to be on the same carbon. So 2 of our substituents are at that lowest number, our lowest number being 1.
Okay.
Does that make sense now?
Yes, thank you.
Okay. And likewise, if we were to change it so we had a methyl group here, then it'd still be 1, 1, 2, 3. Because you want to have your first 2 substituents be at the lowest numbers possible. And then, of course, when we write the whole name out, all of the substituents are done in alphabetical order. Okay, so we have rings, and it's based on the number of carbons in the ring. We have substituents on the ring. If the ring's bigger than the substituents, it's named for the ring. If the substituent is bigger than the ring, then you're actually naming the parent chain to the straight chain. Okay. What if you have more than 1 ring? Okay, more than 1 ring, that would be, well, we take a cyclo to it, but we have 2 of them, so it'd be bicyclo. So it's not a bicycle, it's a bicyclo. Okay, so in this case, we can represent that as in a couple different ways. Okay, so this happens a lot when you have, let's say you had a substituent right here, and then it wraps back around and rebonds to that ring. That's how we get that second ring in the system, and we call it bicyclo. In this first representation, this is a flat representation where we're looking down on top of it. And so it's like you're looking straight down on top of it. Oops, right here, here. However, you can also look at it from a 3/4 view. Instead of looking at it from the top, we can look at it from this direction here. And that's when we get this right here. Okay, these are exactly the same compounds. Notice that they have 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so it's 2 rings, 7 carbons, bicycloheptane. Okay, so our parent is those 7 carbons in the double ring. Now, if we had 7 carbons in the ring plus a substituent, we have to name that substituent. Okay, now, so how do we number these things and how do we name these things? Well, the first thing we need to know is that we have 2 kinds of carbons in a bicyclic compound. We have what are called the bridgehead carbons, which are the ones that where they have more carbon-carbon bonds than all the other carbons. And in the case of this one, we have 3 bonds and 3 bonds to these carbons. Those are what we call the bridgehead carbons, okay? Which makes all the other carbons bridges, okay? And we count the number of carbons in each bridge, but not the bridgeheads, to identify how the structure is put together. So if we look at this side, we have 2 carbons in this bridge. We have the 2 bridgeheads, which go to our total number of carbons. We have 2 carbons in this bridge, and we have 1 carbon left in that bridge. Okay, so that means we have a total of 7 carbons. So we have bicycloheptane, but now we have to identify it as where those bridges are. And we have a special nomenclature for that. You put a bracket, and then you put the largest number first, you put the second largest number second, and you put the lowest number third, and you close the bracket. So we have bicycloheptane because 7 carbons in 2 rings, but we have 1 bridge has 2 carbons, the second bridge has 2 carbons, the third bridge has 1 carbon. So that's how we name bicyclo compounds. It's all about how many carbons are reaching around to reattach to the ring. Okay, so we got that? So let's add one more rule to this, substituents. So when we have substituents on a ring, we actually name our rings a certain way, okay? We always start at a bridgehead. So that's rule number 1 when numbering a cyclo compound. We always start at a bridgehead. And then we always number around the largest bridge first, okay? So this bridge has 1, 2, 3 carbons in it. This is 3. This has 2 carbons in it. This has 1 carbon in it, right here. So we have to number through the largest bridge first. So that's why we have 2, 3, 4. And then we come to our other bridgehead. Then we go around the next largest bridge. In this case, it's the 2. So we have 6 and 7. I usually post recordings pretty quick. It'll be a couple hours today. And then the third, that last carbon all by itself is our last carbon. In this case, we have a total of 8 carbons in our chain. So we have bicyclooctane. And we also have a bridge with 3 in it, a bridge with 2 in it, and a bridge with 1 in it. So that gives us 3, 2, 1 bicyclooctane. But now we have to name our substituent. And because we've numbered our thing through the biggest path first, the second path second, and the third path third, that makes our methyl group on our number 8 carbon, giving us our full name of 8-methyl bicyclo 3,2,1 octane. So does that make sense? And how you number it around the longest bridge first, the second longest bridge second, the third longest bridge third. That makes it unambiguous. You will always locate your substituent correctly. I think I have one more slide on what. No, I don't. I'm going to stop here and we're going to pick up here on next time. Okay. So I'm going to go ahead and stop recording. And then if you want to hang back and ask questions, please feel free.
Thank you.